Hey everyone, welcome back. Here is the second lesson in our journey through probability. We're going to be talking about geometric probability today, which is focused on exactly what it sounds like, geometry. So we are going to be looking at shapes and the probability of hitting a certain piece of a shape. So really it comes down to like dartboard probability, if that's how you want to look at it, if you've ever played darts. We'll get into more of that later, but for now go ahead and do these warm-ups and then compare your answers to what I can come up with next. So go ahead and pause the video, do it, and then push play to see how you did. For number one, it says an 8-sided die is rolled. So this is not a standard die, it's an 8-sided die. What is the probability that it lands on a prime number? Well, we've got to think through our prime numbers. A prime number is a number that is only divisible by 1 and itself. So if you think of all the prime numbers within the range of 1 to 8, you would say that 1 is in fact a prime number, as well as 2, 3, 5, and 7. So hopefully some of you guys got the 2. Don't think that prime numbers must be odd. 2 is only divisible by 1 and itself. So that is our event space. There are 5 things within our event space. So we have 5 different options for our event to take place. Our sample space is all the possible outcomes. So there are obviously 8 possible outcomes, so our probability is 5/8. For number 2, it says a coin is flipped 3 times. What is the probability that it lands on the same side the first 2 times? So if you want, you can go back to the previous video and look at all the possible outcomes that you could get when we flipped a coin 3 times. But we can see that it happened 4 times out of 8, or that reduces to 1/2. For number 3, it says, how many solutions does 3x squared equals 4 minus 4x have? Well, that is dependent on, remember this looks like a quadratic, it is because we have an x squared. We can either get 2 real solutions, 1 real solution, or 2 complex solutions, and that is dictated by what we call the discriminant. Remember, the discriminant is the thing that's inside the radical of the quadratic formula. If the discriminant is positive, then you get 2 real solutions, because you can take the square root of a positive number in the real set of numbers. If you get the square root of 0, if the discriminant is 0, then we get 1 real solution, because the square root of 0 is only 1 distinct answer. And then the square root of a negative number would produce 2 imaginary numbers, because we're dealing with the square root of -1 there. So we're going to go ahead and find the discriminant. Remember, the discriminant is b squared minus 4ac. And then we're going to plug in our values to the discriminant and then simplify that. So we end up with 64. Since that number is positive, when I take the square root of that, that is going to give me 2 real solutions. So let's go ahead and get into our lesson for today. Please make sure that you're taking good quality notes, okay? Getting your essential question and all that down. Our goal today is to be able to determine the probability of an object landing within a certain region. So this is pretty straightforward. We're just going to be applying probability to geometric shapes here. So before we do that, let's talk about the different forms of a probability. We talked about this last time briefly. You can write a probability as a reduced fraction. You can write a probability as a decimal, or you can write a probability as a percentage. So hopefully you remember how to convert a decimal into a percentage, and a fraction into a decimal for that matter. But just a quick review. Let's say you have a fraction that's 4/10. Well, that reduces to 2/5, and so we could say the probability of this is 2/5. But if I want to convert that to a decimal, then I have to divide the top divided by the bottom, and here I would get 0.4 because the base is 10 here. That's easy enough. So we could say the probability is either 2/5 or it's 0.4. But if I want to convert this to a percentage, remember, to convert this to a percentage, I basically take that decimal and I move it over 2 places to the right, and so we end up with 40%. So that's how you convert a fraction to a percent, or from a fraction to a decimal to a percent. Go ahead and try this one. It should be pretty straightforward. You can use a calculator to figure out the decimal value. When you use your calculator, you get 71 over 132 produces a decimal of 0.53788. Now, if I said write the answer as a decimal, you would say it's 0.538 because we always round to the thousandth unless said otherwise. But because we want to convert this to a percentage, the percentage is actually going to give us more accuracy. If I convert this to a percentage, I'm going to move that decimal over 2 places, and I end up with 53.788%. Okay, so these are the 3 different forms you can write it in. That's just a quick review of converting fractions to decimals to percentages. Now, when we talk about geometric probability, really all we're saying is if you had a dartboard and you were trying to hit a certain part of that dart with with your dart. And so here's an example of what this looks like. Let's say this is my cheap looking dartboard here. Okay, I've got the actual board behind the dartboard. Okay, now for our sake, we have to be clear here. Because if we close our eyes and just randomly throw a dart, there is no guarantee that that dart is going to be anywhere on this square. There's no guarantee that it's going to be anywhere in this circle. Even there's no guarantee that it's going to be anywhere on the entire wall that you're throwing. You could throw the dart and hit somebody in the nose. So we have to qualify this a little bit. We have to say that if we throw the dart and the dart hits at least the board around the dartboard. So the dart is at least going to hit inside this square somewhere. If it doesn't hit inside this square, then we don't count it. We're not considering it as part of our probability. We reset. And so it's like saying, hey, I'm gonna bet you $5 that you can't hit the bullseye, right? And so your friend throws the dart and completely misses the board altogether. I mean, it was horrible. And so you, as a good friend, decide, you know what? I'm going to give you another shot. We're going to pretend that never even happened. I'm going to let you go until you at least hit the board that the dartboard is mounted to. All right, anyways, the dartboard is 15 inches in diameter, so that means the circle is 15 inches in diameter, and it's sitting on a board that is 18 inches in length, so this square board is 18 inches by 18 inches. Its bullseye is 2 inches in diameter, so this guy has a diameter of 2 inches, and a dart is thrown and hits within the board, so that's what I was just talking about. It has to hit within this square box at least. For part A, it says, what is the probability of hitting the dartboard? So the square board is not the dartboard. That's just the board that it's mounted on. What is the probability that it's going to hit the dartboard? Well, the dartboard is the big circle. So our event space is hitting the dartboard. Our sample space is hitting anything in the square. So if you think of this as area, I'm going to go ahead and find the area of my sample space. My sample space, again, is the area of the square. Okay, the sample space, remember, is the denominator. It's the square. So the area of the square would be, what, 18 by 18. Right? So we'd say 18 times 18 for that, which is 324. The event space is the thing that I want to have happen. So the thing that I want to have happen is to hit within the circle. So the area of the circle, the larger circle, is the event space. And remember, the area of a circle is pi r squared. And since the diameter of that circle is 15 inches, that means the radius is 7.5. So it's pi times 7.5 squared. And then when I calculate that all out, I get 176.715. When I set up my probability, remember, it's always event space over sample space. So the probability of hitting the dartboard would be 176.715 over 324. And then we just type that in our calculator, and we end up with 0.54542. And then we're going to convert that to a percentage, which is 54.542%. Again, pay attention to how the wording of the problem is. If it says round to the nearest tenth or the thousandth or whatever, then you'd write it in this form, decimal form. If it says write it as a percentage, then you'd write it in this form. For part B, it says, what is the probability of hitting the bullseye? So now our event space is this little circle here, but our sample space is still the whole big square. So our sample space is exactly the same, but our event space is now the area of the little circle. And remember, the area of a circle, again, is pi r squared. Because the diameter of the little circle is 2 inches, that means the radius is 1, so it would be pi times 1 squared, and that would be 3.14159, blah, 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 blah. It's whatever pi is. And so our probability is going to be, the probability of hitting the bullseye, is going to be 3.142 over 324, which is 0.969%, less than 1% probability of hitting that dartboard. And again, I want to be clear here. This is just randomly throwing the dart. It's not a professional playing darts. Obviously, the professional playing darts is going to have a higher probability of hitting that bullseye because they have a skill and a talent behind this. This is randomness. This is closing your eyes and throwing the dart and hoping for the best. All right, let's go ahead and go on. Here are 3 examples or 3 practice problems that I would like you to do on your own. I want you to find the probability of hitting the bullseye. Now, the bullseye in each of these cases is the red region. And then we know that you are at least going to hit within the black outline of each of these. So go ahead and pause the video and then come back after you're done solving these problems and see how you did. For number 1, our goal is to hit the red triangle. And so that is our event space. But the sample space is the square. So the sample space is going to be 5 times 5, which is 25. And again, our event space is trying to hit the triangle. So the area of a triangle is 1/2 base times height. So that'd be 1/2 of 2 times 2, which is 2. And so our probability would end up being 2 out of 25, which can convert to 0.08 as a decimal, or 8%. For number 2, our event space, the thing that we want to have happen, is hitting the square, and our sample space is hitting the circle. So our sample space is going to be the area of the circle. Now remember, the area of a circle is pi r squared, so you can see that the radius here is 3. So it's going to be pi times 3 squared, which is 9 pi, or putting it in decimal form is 28.274. And then our event space is the square. So the area of that square is going to be 2 by 2. I know this little 3 here makes it a little confusing. The 3 represents the radius of the circle, not the height of this quadrilateral here. The height is a square, and we're assuming that here that's a square, but 2 by 2, which is 4. So the probability of hitting the bullseye would be 4 out of 28.274, which is 0.14147 or 14.147%. Number 3 is a little bit different. Some of you might have said, well, I can't solve that one because I can't figure out the areas. Well, that's okay. You don't need the areas in this case because this is actually dealing with sector area and a portion of the circle. And it's pretty straightforward. It wouldn't matter what the radius is because this area, this red area, is dependent on the same radius as the area of the circle. So we could just say the event space is just this much of the circle. Well, how much of the circle is that? That is 135 degrees out of the sample space. Well, what's the sample space? The sample space is all of the circle, which is represented by how many degrees? 360. So we can say the sample space is going to be 360 degrees, and our event space is going to be 135 of those degrees. And so our probability would be 135 out of 360, which is 0.375 or 37.5%. But that's going back to the idea of sector area. Remember, the first thing in sector area is to figure out the portion of the circle. Well, we have 135 out of 360. If you went ahead and found the areas of the sector and the area of the circle and divided it all, we would still end up with the same probabilities. All right, let's go ahead and take a look at another problem. This is another practice problem, and it's a little bit more difficult in the way that it's worded and the way that it looks, because now we're talking about not just hitting a bullseye, we're talking about hitting other regions. And so go ahead and pause the video and see how far you can get on each of these things. and then push play and see how you did on each of these. All right. So in these problems, it's skee ball, right? You go to the arcade and you see those games where you're rolling the little tiny ball up the alley and you're trying to get it within a certain region, and you get a certain amount of points depending on which region you get it in. And obviously the bullseye, the red part, is going to be the most points. Now here's the point breakdown of this thing. If you get it in the blue region, you get 10 points. If you get in the yellow region, you get 20 points. If you get in the red region, you get 50 points. And then we have some information here. We know that the length of this square is 28 inches, and the diameter of the big circle is 24 inches. The diameter of the yellow circle is 15 inches, and the diameter of the red circle is 7 inches. Now here on number 4, it's saying, what is the probability of getting 50 points? In fact, this is probably going to be the easiest problem out of all of this. If I want to get 50 points, that means I need to get it in the red region. Well, the red region is going to be our event space, so we're going to find the area of the red circle, and then our sample space is going to be the area of the square. So it would be, the area of the red circle would be pi times 3.5 squared, because the radius is 3.5, so pi times 3.5 squared, over the area of the square, which is 28 times 28. When you do that, all worked out, you end up with 4.909%. Number 5, it says, what's the probability of getting at least 10 points? Well, think about it. If you want to get at least 10 points, that means you could get 10, 20, or 50 points. Now, what you might think you need to do is find the area of the blue region plus the area of the yellow region plus the area of the red region. And that's true, that would be your event space. But really, when you add up the blue region, the yellow region, and the red region, you're just getting the area of this big circle here. So the probability of getting at least 10 points is going to be the area of this big circle over the entire square. So the area of this big circle would be pi times 12 squared, because the radius of the big circle is half of 24. So pi times 12 squared, all over 28 times 28, and that works out to be 57.703%. Now, the next problem is probably the most difficult one on here. It says, what's the probability of getting 20 points? Not at least 20 points, but exactly 20 points. So we need to figure out the area of the yellow region. If you just found the area of this middle-sized circle here, that is not the yellow region. That's the yellow region plus the red region. So how could I find the area of the yellow region? Well, I would have to find the area of this mid-sized circle and subtract the area of the red circle. So it would be pi times 7.5 squared, that would be the area of the middle circle, and then minus pi times 3.5 squared, that would be the area of the red circle. So that's going to give me my event space, and then the sample space is still going to be the area of the square, 28 by 28. If you do all that properly, you should get 17.631%. And if you're having any questions on this, please check in at office hours and ask me for help so I can walk you through it a little bit more. For the last problem here, number 7, it says, what's the probability of getting 0 points? Well, there's nothing here that says you would get 0 points. 0 points is if you don't hit the blue, the yellow, or the red. In other words, if you're hitting the white region here. So what you're going to have to do, actually there's a couple ways of doing this. What you could do as one option is find the area of the white region. So you could find the area of the big circle and then subtract that from the area of the square, right? That would give you the area of the white space, and then divide that by the sample space, which is the area of the square. So just if you were thinking of an equation, it would be area of the square minus area of the big circle, and then all of that divided by the area of the square. You could do it that way. But another option is to look back on number 5. It says, in number 5, it says, what's the probability of getting at least 10 points? Well, getting at least 10 points, if you got at least 10 points, that means you scored because there's no other option. So the only other option, if you didn't score at least 10 points, that means you scored 0 points. That means question number 7 is the complement of question number 5. To score 0 points is exactly the opposite of scoring at least 10 points. And if you remember back from the previous lesson, 2 events that add up to the entire sample space are called complementary, which means that the probabilities are going to add up to 100%. So, since it's a 57.7% probability of hitting inside the big circle, then it's going to be a 42.297% probability of hitting outside the big circle. And so again, if you have any questions on this, please check in at office hours and ask me, and I would be glad to go over this. But that wraps up this lesson in geometric probability. So go ahead and do the example, the practice problems below this, and I will see you again next time.